Okay, so in this last part, I just want to walk through some basic examples of extending now this nomad simulation schema. So the idea is that, okay, like we start to develop a parser, as Nathan was describing, and so we make a package from this template, and we're developing our parser. And then at some points, we're going to need to decide, um, or first utilize this nomad simulation schema. So for consistency with the central nomad schema, and for that we sort of made this decision tree, which might help. I'm gonna, if you click on it, it'll zoom in. Although I don't know, my computer is having trouble, so I'm not going to go through the whole thing. But it sort of is using what the structure that Chema like outlined to direct you to the parts of the schema that you should like look at. So it's sort of like you need an input or output. Okay, you need an input. Does it have to do with the geometric space or the mathematical model? Then you go to one way or the other, and eventually you're going to get to some point where it says, is this supported already? Is this item supported already? This data that this metadata that you're trying to store, and if it is, then you should use the Nomad simulations. And then, of course, if it's not, then you need to extend Nomad simulations in some way, and you can do that directly in your parser plugin. So the template will. So during the template creation, you can create both a parser folder basically and a schema packages folder. So you always want to do this for sort of consistency, and then also maybe you don't anticipate that you'll need to extend the schema, but then later you realize you do, and then you can put your schema files into this schema packages folder. And I sort of just try to categorize the different types of situations that you might encounter when you're writing a parser and then developing a schema. So the first case is obvious. It's just okay, the Nomad simulations completely covers all the quantities that you're trying to store, and in that case, you can just directly use the schema classes from Nomad simulations. And this is exactly, the implementation is exactly in parser plugins. And then I just put a link here to, this is just going over to the documentation version of what Nathan just presented. So this lays out Nathan's presentation, but so you can go back and there's a lot more details here and information that you can grab. And the second case is sort of what I would call semantic extension. So you may want to use a class first that already exists in the Nomad simulations, but you might want to sort of refine a bit the context within your domain. And I'm going to show an example of this in a second. And the other case, maybe the more obvious case, is that, okay, I'm trying to store something that is completely not represented, and now I need to just create a completely new class or what we should call section within the schema. And then finally, these normalization functions that we've been talking about. This is a very useful part of extending the schema, as was already sort of hinted at as we went along. And we can leverage these to perform various tasks, and importantly, as Nathan pointed out, to simplify the code in individual parsers. And this is really, really important for interoperability. And so so I'm just going to walk through this page, and I'm just going to try to point out the overarching concepts of these examples, and then you can come back and look more in detail later. So the first thing is, again, like when you develop a schema. So you're going to, when you use this template to start a parser plugin package, you're going to have this folder called schema packages. And so we could already create a file to start extending our schema. Maybe you can call it whatever you want, but I call it like the parser name and then schema .py. And I just put some imports that you would likely need here. And so actually you don't need to import this. So Chema talked about this a little bit before. It's just, this is sort of putting in the functionalities, the sort of default functionalities. And this is already going to be included in the classes that I'm going to show you are used through inheritance in the examples that I'm giving. The other important classes to import here, coming from the Nomad metadata info, are quantity and subsection. And we've already talked about these a bit, but we've seen a little bit of code actually in how this works in Python. But so these are going to be responsible for populating the attributes underneath our sections within the schema. And so, okay, so the first example is quite just sort of made up, but it illustrates some fundamental points. So imagine that now that we had, okay, I'm trying to develop a parser, and let's say I have some HDF5 file format, and this HDF5 schema. So this is the way that the HDF5 file is structured, is according to some schema, and it contains this information. So these are it has sort of its own schema, and this is exactly what Nathan was talking about. Basically, in parsing, we want to map this between this structure, this tree structure, and the nomad tree structure. But instead of this file coming directly from a simulation package, imagine that like this is a file that's sort of created from some raw simulation data and then placed in by a researcher. And for that reason, we have some additional quantities here. So yeah, so the important thing here for what the example I'm going to show is simply that that there's some additional software, which is the HDF5 generator, that was used to create this file. So we have both the simulation program and the HDF5 generator. The author is not important for this. And then we have a version which is in like a semantic versioning, so it's stored as an integer. So this isn't important. And so the first sort of assignment was just to ask, based on what you've already learned, like which of these quantities that I just pointed out, so these three quantities, can we store in the simulation schema with the classes that we've already learned about? So just think about that. The program, we've already talked about this program section. So we have this in under simulation. There's this, it's actually in the base simulation class Chema showed in his presentation. There's this program subsection, and it has attributes, name and version, but it also has some other attributes. And so we can directly populate this, and this is exactly what sort of we've already seen. So I just wrote sort of a mock parser here. So parser name, parse, this is sort of what Nathan was showing us. And then this is essentially what Chema showed us in the beginning. So we can populate this and then put it into the archive. Okay, so that much we already learned, so I'm just going to brush over that. And then the HDF5 generator is a new quantity, right? So this is not exactly the simulation program. And remember that program in our schema is not a repeating subsection. So really, we can't store both this and the simulation program under program. And so we need to extend the schema to account for this new software that we're trying to store the schema for. But this HDF5 generator actually has a lot of similarities to the simulation program. So the first question we should ask is if we can use this class to store the HDF5 generator information. And so I just did a little trick here where I imported the program section, and then I instantiated this, and then I just print out. So you can print out the quantities or the quantities in subsections, or I guess these are just the quantities living in this section. And here I can see, okay, I have name and version. And if I go through and look what these other quantities are, it really makes sense. It's just a general software class. So what I need to do then, and this is the next exercise, is to write down a new section that extends the simulation schema to include a subsection called HDF5 generator, and this should be of type program. And just to give you a hint, because we haven't looked at much code, in the base simulation class, this section, this is how the program, the original program section was defined. So we say program is equal to subsection, and then we say it's of type program, and this is a non-repeating subsection. Okay, so I'm just going to show you the solution. So what we need to do, importantly, we need to, inside our parser plugin, we need to go to this schema extension file. So under schema packages, this is where we're going to extend our schema. And now we need to make a new class, which is called simulation. And this class is going to inherit from the NOMAD-Simulations class. So here you could also put this import up top, but here I just imported the entire NOMAD-Simulations, and then I just put the path to the simulations definition. And this, so now I have a new class, and this is going to be identical to the class in NOMAD-Simulations, but I'm just going to create a new subsection, which is HDF5 generator. It looks nearly identical to this, except for now this definition is going to be of type program. And this program type is coming from NOMAD-Simulation. So I'm not redefining this. I'm just reusing the program class, and I am placing it into a new section. So now there's two sections in our simulation. One is called program. One is called HDF5 generator. They're identical though, and they can be populated individually. So I'm just sort of going to go over this. This is sort of repetitive. Skip over this, but you can look later. But then I do the same thing in this mock parser, but I just populate now this HDF5 generator. It's of type program. I just want to point out that now I'm importing simulation from my parser plugin, but the program definition or class is coming from the NOMAD-Simulations package, right? Because I didn't redefine this, but I did redefine this. Okay, so yeah, so let me do a couple more examples, and then we can end with a little brief thing about workflows. So the last thing is just to define this HDF5 schema version. I actually think I'm gonna let me actually skip this and just do the last example. So this is very similar. It's just about defining a quantity essentially, which is basically the only thing I want to point out here is the sort of syntax. So when you define a quantity, you have to define the type and shape, and then you want to put a description. And I actually put here already a link to, you can link directly to the NOMAD-Simulation source code. And then you can look through some examples of quantities that are defined, the types of strings, and the types of the data types that are used. For example, you can use this enum, which forces it to be of certain strings, and so on. So you can browse through this on your own and learn how this type of schema is built up. But let's, in the last couple minutes, let's look at this last example. So this last example is sort of using, or is using this same VASP run XML parser, which I say is fabricated, but it's sort of like it's in the transition of being working, and so we'll probably remake this example so it's actually a working example. But right now it's sort of just a another mock example. But let's imagine that now, in thinking about the code that Nathan showed. So I can show it here really fast to remind you. So in this parser, it basically just had this parse function, and then this XML reader was in charge of grabbing the data from the file, and then we we just set archive.data equal to simulation, and then we just put all the information, and we directly grab this information from the corresponding place in the XML file. So now imagine in that example that we parse the system information in the program, right? That was at least what was shown here, but we haven't yet parsed any output information, okay? And then I'm also going to just assume that I have grabbed these outputs, so these different energies. So there's 3 different energies, total energy, and then these 2 energy additional energy sub contributions, so the contributions to the total energy. And now I just want to look to see how if if I need to extend the schema and how I should extend this. So in Nomad simulations, there's already some energy definitions here. So there's a base energy class. This is some abstract class. So all the energy classes inherit from this, and it's sort of just responsible for defining the appropriate unit. So we define the value here with units of joules, and then we never have to define this value again. It sort of just is passed along to all of its children. We have this energy contribution class, which I don't want to go into, but basically it just allows us to link the each of the an energy contribution to the total energy to a specific component of a model. So it just means if I have terms in my Hamiltonian and I want to store energy contributions from these particular terms, then I don't have to redefine them in the schema. I can just link them over, and this is done using references, which was sort of briefly mentioned by Chema, but that would be something that is out of scope for today. And then we have this total energy class, and this is a base energy, so it has this value. By the way, all these properties I didn't mention again, are inheriting from this physical property. So all output properties share this generic class definitions, and this was introduced by Chema, so you can go back if you didn't remember that part. But in any case, the important thing for this example is that the total energy definition, it has this value, but it also has this subsection called contributions, and this is where we can store any sort of energy contribution. And again, this is sort of utilizing this idea of polymorphism that Chema also sort of mentioned in passing. Okay, so what is the assignment then? So basically these two quantities that were parsed, these can be classified as double counting energies. So the idea was, okay, we want to extend the schema. Let's assume that these are not already accounted for in the schema. So we have some outputs. We need to define these in some way. So we want to add three sections into our schema, one for each of these parsed energies, and then a third, which is like which these two classes inherit from, which is characterizing this double counting energy. So I want like a double counting energy class, and then a Hartree DC class, and then an XC DC class. Basically, that's the basic idea. And so I just here's the answer here already. So this is very simple. I just make these three classes. They have basically nothing inside because all the information is, so first of all, this is inheriting from energy contribution, which is then inheriting from physical property eventually, and for base energy. So this has the value with the appropriate units, and also all the functionalities of physical property. So that's very simple. I can just put these classes and then I'll be able to populate them. But the interesting thing here, so these two parsed energies, so actual energy, like something we're going to populate, these inherit from double counting energy. And then what I can do is I can utilize this normalized function. And I utilize this normalized function to set the type. So type is something that's defined in physical property, which helps to like characterize a certain output. And so I can set this automatically. If it's not set by the parser, I'm going to set this automatically to double counting. And actually, I went further to overwrite the type quantity so that it has to be of type double counting. So if in the parser, for some reason, someone sets one of these energies to a type that's not double counting, then you'll trigger an error, basically. So this is sort of a stupid example, but it's demonstrating that I can utilize this normalization and inheritance to sort of automatically do some checking and some characterization or some other bookkeeping or whatever I want. And this is sort of one idea of how we can extend these classes. Yeah. And then finally, the idea would be we can go further. So we could say, okay, now this total energy class, actually, for my use cases, I'm always doing a decomposition of the total energy into contributions. And so I may want to automatically create and populate some class which is like the remainder of the total energy, which hasn't been explicitly populated in the parser. So in this exercise, I'm asking to implement a new extend the total energy class from NOMAD-Simulations so that it has this normalization functionality. So I want to calculate the difference between the total energy and any contributions that I populate uh, throughout parsing, and then I want to store this remainder as a contribution to the total energy. Okay, so this is the last part. So just I created a new class called unknown energy. So this is going to store the remainder of the contributions. And then again, I'm extending the total energy class. So I create a new class total energy. This is inheriting from the NOMAD-Simulations total energy. And then this is identical to that class, but I have a normalization function which then does some calculation. So first it checks if this total energy has a value, and if this total energy has some sort of contributions, it then loops over these contributions and makes sure that each contribution has a value, and then it just calculates the okay. I changed this at the last minute, and I messed up this code. Anyway, the value should be set in advance before this loop. There's some mistakes here, but I hope the idea is clear. The code is supposed to calculate this value, and then what it's going to do is create for each contribution. For each total energy, it's going to create a new contribution, which is unknown energy. And then the main idea, lastly, is when I implement this in the parser. So I'm just going to brush over this because we're running out of time, but you can look at where the imports are coming from. This is important. When I implement in the parser, I'm populating the Hartree energy and the XEDC energy explicitly, right? That's part of the parsing. I'm doing this sort of manual setting, as Nathan was explaining. But I don't have to do anything about this unknown energy because this is being taken care of by this normalization function. And again, this has this dual effect. I mean, so this is sort of a silly example, but it has this dual effect of both simplifying the parser. So I'm simplifying the parser in some way, and I'm standardizing things. So now the total energy is always going to have this unknown energy, which is exactly the remaining part of the total energy decomposition. Um, so I hope that gives you like some small ideas of how these normalization functions can be utilized, and we have much more interesting examples that actually live and will be continue to be developed in the NOMAD-Simulations packages, and probably will add that there's some links to examples in this page later on because we're sort of continuing to develop this.